Hi everyone, welcome back to my channel. If you have ever wondered how Google Maps find the shortest routes or how networks calculate the best path between every pair of locations, then this video is for you. Today I am going to explain the Floyd-Warshall algorithm in a simple, visual and easy to understand way. Don't worry if you are new to algorithms. By the end of this video, you will understand it clearly. Let me start with a simple question. Imagine you're planning a road trip. You don't want just one shortest route. You want to know the shortest route between every city and every other city. This is exact problem appears in road networks, computer networks, airline routes, or else social networks. And the algorithm that solves this problem is called the Floyd-Warshall algorithm. So, here's what we will cover today. First one is purpose of the Floyd-Warshall algorithm. Second one is why we use an adjacency matrix. And the third one is step-by-step distance updates. And the last point is a small example showing all pairs shortest path. So, let's get started. Now, let's clearly define the purpose of Floyd-Warshall. It calculates the shortest path between all vertices. It works even when edge weights are negative. As well as it uses dynamic programming. And it is simple in logic but powerful in result. It does not work if the graph has negative cycles because distance would keep decreasing infinitely. So whenever a problem says find shortest path between all pair of vertices, your answer should immediately be Floyd-Warshall algorithm. Now let's talk about how we store the graph. Floyd-Warshall uses an adjacency matrix. So what is an adjacency matrix? It's a 2D table where rows represent starting vertex as well as columns represent destination vertex. Each cell stores the distance from one vertex to another. To do that, there are few rules. The first one is any vertex has zero distance to itself because no movement is required. In the matrix, diagonal entries where row equals to column are always zero. And the second rule is if there is a direct connection between two vertices, the matrix cell stores the weight of that edge. And the third rule is if no direct path exists between two vertices, the algorithm treats the distance as infinite. This signals that the vertices are not reachable directly. Through Floyd-Warshall will later check if an indirect path exists. These rules set the initial conditions for the Floyd-Warshall algorithm. The algorithm then iteratively updates the matrices by checking if going through intermediate vertex provides shortest path. Now let's break down the step-by-step process. We use three loops. They are K, I, J. K represent intermediate vertex, I represent starting vertex, and lastly J represent ending vertex. For every ij pair, we ask, is the path from I to j shorter if I go through k? Now refer this code. If current distance is greater, then we update the matrix. This happens repeatedly until every vertex has been used as an intermediate. That's why the algorithm is systematic and guaranteed to work. Now let's go through a small example carefully. So in this table you can see vertices are A, B, C and D. Now as step 1 we use A as intermediate. Check all paths that go through A and update distance if shorter. So this is the answer we get. Now as step 2 we use B as intermediate and do the exact same. Now you can see A to B to C becomes shorter than A to C directly. Step 3. Using C as intermediate. Now you can see many distances reduce further. And now step 4. Using D as intermediate. Now you can see final optimization happens. After all these steps, the matrix now stores shortest path between every pair. Finally, let's talk about efficiency. Time complexity. The algorithm runs three nested loops, one for each possible intermediate vertex, one for each source vertex, and one for each destination vertex. That means for a graph with v vertices, the algorithm performs roughly v multiplied by 3 operation. The cubic growth makes it practical only for small to medium graphs. For every large graph, the runtime becomes too slow. And the second one is space complexity. The algorithm stores distances between every pair of vertices in a matrix. Since we multiplied by two pairs, the memory requirement grows quadratically with the number of vertices. This is manageable for graphs of moderate size, but memory usage can become heavy for every large graph. So these algorithms are best suitable for small or medium sized graphs. The cubic runtime is acceptable when the graph isn't huge. And for dense graphs, since Floyd Warshall considers all pairs of vertices, it's efficient when many edges exist. Sparse graphs often benefits more from algorithms like Dijkstra's run from every vertex. If you remember just one thing, remember this. Floyd Warshall is about checking every possible path through every possible intermediate vertex. Once you understand this mindset, the algorithm becomes very easy for you. So, if this explanation helped you understand Floyd Warshall clearly, like the video, subscribe, share it with your classmates. Thank you for watching, and I'll see you in the next video.